Thank you. Hello, everyone. This is a very informal talk, which is code for ask lots of questions and interrupt me, and that's totally fine. It's also kind of like an experience report. I write a lot of Go, and these are some things that I have found that are useful, maybe. We'll see. I'm Peter. It doesn't matter who I am, really. OK, here's the outline. I'm going to talk about actors, basically, which is, for me, like a quite general concept, and basically two ways of structuring them internally. Then like different ways to run them in the calling context, and then taking even a further step back, ways to orchestrate components in a program. So let's start with actors. Whenever I write programs, they all tend to take the same form, and maybe this is something about the sort of work that I do or the sort of programs that I write. But they all seem to be organized in the same way. I'll have a bunch of components that are largely independent, but have like dependencies to each other. And I want to run them kind of like on their own, but be able to have failures in one maybe be reflected in others. So to make this more concrete, let's say I have a program that, a server that's running, and it needs some storage component. And this storage component is going to be backed by disk or by memory or something. It doesn't really matter. So I set that up. And then I have some kind of state machine, some kind of business logic that executes on top of it and uses the storage component for persistence. OK, so far we're pretty general. So there's some dependency there between the state machine and the storage component. Maybe that's expressed as an interface or something. It doesn't really matter. Then in order to interact with the state machine, of course, you need some kind of like API and maybe some kind of, so that your consumers are going to like ping you through, and maybe some kind of cron task that's running all the time that is doing some sort of cleanup or doing things on a regular schedule. This happens quite frequently for me. And then, like with all these components, you also want something that's going to respond to external events to be able to tear everything down. And for me, that's usually just some kind of Control-C handler, right? Or maybe there's some other way that you can wire in a shutdown signal, maybe through an admin endpoint or something. And that's going to need to, in the ideal world, talk to all these things and be able to kill them, right? So this is the framework of the talk, I guess. Most of my programs look something like this. Maybe yours do too. If they don't, I guess you can kind of space out. That's cool. So let's zoom in for a second on one of these things. I picked the state machine because it's maybe the most interesting. How do we actually build components like state machines? What does the structure of that thing look like? Well, for me, a lot of the time, it's a struct. And the struct is going to close over or capture some kind of state. In this example, I have a state. It's just a string. It could be anything. You could imagine there would be I probably should have put this in there, but like a reference to the storage layer or something, or a whole bunch of other bits of state. Whenever you have a component that has state, there's lots of ways to model it. The most naive way is probably with a mutex or something, right? So you could have a mutex here, and then every public API method would lock the mutex, do the mutations, and release it. One thing you find quickly is that this is great for certain classes of problems, not so great for others. What's the Go proverb? Use channels to orchestrate and mutexes to share access to data or something like this. So a lot of times you want to orchestrate. You want to have a way to establish some kind of serialization point without using the low-level primitive of a mutex. So the actor model that I see all the time, and that I bet almost all of you have probably seen, is where you have a struct with some channels embedded into it. And each of the channels represents some kind of thing you want to be able to do with that struct. So in our state machine here example, we have a foo and a bar chan, which are both chans of foo requests and bar requests, respectively. This is a bad example. You might think of these as being like a set and a get, or like a transition and an inspect, or something like this. So those are our channels. In order for this to work, we typically have a method on the struct called a loop or run forever or something like this, which is this very typical for selects thing, the structure that you see all the time. And in the for selects, you're going to have a case statement for each of the channels that you can receive requests on, as well as for this quit channel. It's just a way of tearing it down. And so then our public API is going to have a bunch of methods. Foo, for example, let's say that it doesn't take any input and it returns an integer. And so the way you would interact with this thing is you would create some kind of channel to receive the response out of the structure. You would pass that along as part of the foo request, and then that request would go into the loop method, which is running in its own Go routine, say, acting as a serialization point for the actor, doing all the work, and then returning the response out. So I see this all the time. I'm sure you've seen it in other programs as well. What's nice about this is that it gives you like synchronization for free, in a sense. You can write your code, your handle foo function here, in a completely straight line, imperative way, and you don't have to worry about fine-grained locking, which is really nice, right? You have a single go routine that's managing all that for you. So I see this a lot, and it's fine. It's kind of fine. But it gets tricky when you have a lot of public API methods that maybe compete for cognitive load, or maybe the stuff you're doing in there is quite complex. So I stumbled across this other pattern in the company I was at previously, which I thought was super elegant, and I'm using it more and more, so I just want to like share it with you. I don't know if it's advanced, but it's like interesting at least. Rather than having a set of channels, one per public API method, what you can do is have a single channel internally, call action chan or something like this. And importantly, it's a channel of just like empty functions. So the functions are going to be executed in this way rather than selecting on every single type of request you can receive. You're just going to select on the action chan. You're going to pull a function out of it, and then you're just going to run the function. And you don't care in the loop method what you're doing in there. You're just running it, and you're basically restricting the loop method to be only the thing which is acting as a serialization point, only mechanics, no business logic really. Yes?
Is it implied here that the function closes over the state, or are you supposed to?
The question is it implied that the function closes over the state? And yes, we'll get to that in 0 seconds. So this changes what the public API methods do. So here, in the previous example, foo was like just creating this request object, which you had to like define and like fill with fields and then ship it off and then get a response back. Here, instead, what you do is in your foo method directly, you interact, you pass this function closure, and you define the function closure in the foo method. And then you pass it directly, and you access the members of your struct as if you had isolated access to it, as if you had synchronized access to it, which you do. Because by passing it as a function closure, it's getting executed in the context of this other go routine. And so I like this a lot, like maybe too much, maybe I haven't found the limits of it, but it's like super nice because not only are you, there's so many benefits, not only are you making the loop method do exclusively mechanical work, like synchronization work, and have no concept of business logic, you're also moving all the business logic into the function that's called for the thing that you're doing, right? Because previously it was like separated. You were in this function, you were just creating the struct, the request struct, and then you were having some other handle foo function that you would have to call in order to do stuff. So I like this a lot. And you can imagine when your input-output gets like much more sophisticated, then you can keep all of that business logic in this function as well. And I think the next slide, yeah. So here's an example of it in real life, I guess. OKLog has a couple of components that are built this way. And this is actually, if you can read it, it's like an API. So this is a thing that serves HTTP. And so here's one of the HTTP handlers on this API, handle commit. It doesn't really matter what that is, but you can see it matches the HTTP handler func interface. And so what it does at the beginning is it sets up all of these channels which represent all the possible output things that can come out of this commit call. Then it passes this anonymous function, and it like has access not only to the reader and writer from the HTTP request and response writer, but also all the member fields which are synchronized. And so I can do all my work in here. I can mix and match from these two like sources of truth, do my mutations. It's all fine. Whenever I need to like signal back to the caller and like tell my client that I want to like have some change or return some result, then in the case where I don't need to actually convey any information, I just need to convey a signal, then I can close the respective channel. In some cases, I need to send an error. In some cases, I need to send an integer. But it's really nice. It's like pretty straightforward. And then here on the right, you see like how I determine what to actually respond to. It's just a big select block. So that's cool. I like this a lot. So yeah, there it comes. Should have made that animation a little bit faster. So the two models of actors. One is like having a bunch of channels. It's like kind of intuitive. It has a clean separation of concerns, very explicit. But the logic, the business logic is separate from the actual methods, the public API methods. There's more types and fields you have to define, so it's a little bit more verbose in that way. And it ends up mixing mechanics, like the mechanics of synchronization with the business logic, which is maybe not so great. So if you have relatively few API methods and your like pattern in and out of the actor is like request response, and maybe it's okay. And I still use it all the time when these things are true, but kind of like for easy cases. On the other hand, if I have more complex cases, I really like this other one. It's maybe not totally obvious when you see it for the first time. You're like, oh, I haven't seen that. But you get to co-locate your method and your logic. You have fewer types and fields you have to define. You keep your mechanics and your business logic totally separate. So I find when your situation is more complex, this is a lot nicer. Maybe. Your mileage may vary. OK, actor stuff. Number 2, running stuff. So we have a state machine, and I didn't show you the constructor. But this is probably what it looks like in that initial version, or sorry, in the action chan version. We construct the state machine. We give it some initial states. We have to populate the channels that are inside of it, allocate them, I mean. And then probably we have something like this, where we're going in the constructor a loop method, which is going to act as a synchronization point. And then we return the object. So this goroutine is kind of hidden. By constructing the object, you're automatically launching this goroutine that's kind of running. And I see this all the time, too. I think this is what a lot of people default to. So here's our loop method. And the way we shut this down is by selecting on this quit chan. So whenever anybody sends a signal, in reality, it's going to be a close, I think. Yeah. Whenever anybody closes a quit chan, we're going to see that signal in the loop method, and then we're going to return. So here's what a public API stop method might look like. We would just close the quit chan. This is like the most obvious way, the most obvious way of doing this, maybe. But there's problems here, right? Because first of all, this isn't reentrant. I can only do this once. So when I construct the state machine and then I stop it, like what do I do? If I wanted to start it up again, I couldn't. There's some other tricky stuff to this. So maybe there's the other tricky thing is I can call stop, and it'll close the quit chain, but then it'll just return immediately. And so I don't really know if the goroutine is actually stopped or not. Like I've signaled that it should stop, and it probably will. But if some other other case statement in the select block is like deadlocked or running for a really long time, then like the fact that the stop method has returned hasn't really told me anything. So we can kind of improve this a little bit. If instead of just having a chan of structs as just a signal, we can turn it into a chan of structs. Then this allows us to, instead of just closing it to signal stop, it allows us to send a channel along it and then select on the channel in the stop method. And then in the loop method, when we receive that channel, we can close that channel as sort of a back signal, right? And what that tells us is that I have entered the case statement. I have seen that you've asked me to quit, and I'm like closing the little request you sent me. I'm telling you that I'm about to quit. So this is an improvement, I think. It costs you a few more lines of code. And like if you haven't seen this before, again, it'd be like, well, what's going on here? But what this allows you to do is have like a better step towards determinism, which is helpful in tests. Although, if I'm being completely like truthful, it's actually not totally deterministic, because it could be that the scheduler would run this like close line, and then for whatever reason never get to the return, and the goroutine would still be allocated and running. So okay, technically that's possible. So this like hidden goroutine model I see all the time, and I think it's okay, especially in this form. But I think in a lot of cases there's an even better way, and that is to not do any of this work at all, right? To just have the state machine be this idle, plain old blob of data when it's returned from the constructor, and then to require the caller to run some kind of run method themselves. And probably they're going to want to do this in its own goroutine, but that's fine. You can just like document it in that way. And then this gives the caller like a certain amount of power. In this case, I've had it take a cancel receive only chan of empty struct, which it can then select on in the select block in the same way we selected on the quit chan previously. This means that the caller has the complete, like, on the one hand, like power and flexibility and freedom, and on the other hand, responsibility to orchestrate the running, the goroutine of the state machine, however the caller sees fit. And I think in a lot of cases, this is actually quite a bit superior, not only because we have like absolute determinism, because we can set it up however we want, that makes testing easier. It also kind of aligns with this general idea about context. So if you wanted to use a context, you can do it in exactly the same like style. You pass a context, and you select on the done chan. Did you have a question? Or was that your question? OK. Yeah, so I think this is actually kind of better in a lot of cases. So the go loop, the hidden go routine, it's like obvious, I guess. You kind of intuitively see it that way. It turns your component into this like completely self-contained thing. So you can just create it, and then you can, it's automatically started, and then you can stop it, and then it kind of shuts down. And so in that way, it encapsulates some kind of its own life cycle. But it's tricky to get determinism in that model, and it's tricky to make that reentrant. So even in that second form, I couldn't call stop twice, really. There's a ways around it, but it's like a lot more code, and it's tricky to copy and paste all over the place. So if you have a simple component, when it's like more important than it's easy to understand that it necessarily needs to be like totally correct, then maybe this is fine. On the other hand, this run style where you force that job to the caller, it's definitely more work and it's more state for them to track, but there's less scaffolding in the component. There's one fewer channel. There's less there's not a stop method. There's all this stuff missing. You get straightforward determinism, much easier to test. So for me, when the components become a bit more complex and they need to be a bit more flexible, I find this is better when correct is more important than easy. Okay, down to the bottom, orchestrating stuff. So we're back to our diagram here. We've been focusing on the state machine. But all these things kind of have the same model, modulo the storage, right? That's kind of just sitting there probably. But everything else is something that's running, and it's doing stuff, and it's responding to external events, and it's like changing state somehow, and it's talking to other things. So when I write programs, I generally, like in the explicit dependencies in a large func main style, I generally wire all this stuff up in my func main, and build all the components out, and then like go the specific things that I want to run. So in this example, what do we have? We have like a state machine, an HTTP API, a set of cron tasks or something, and then the Control-C signal handler, right? So maybe it's going to look something like this, right? We have some setup phase in our func main. We create a context at some point. The context comes with a cancel func. And then we're going to have a state machine. Let's say we went with the run method. We're going to need to go sm.run, pass a context to be able to cancel it later. At some point, we're going to have to go HTTP listen and serve to serve our HTTP API, which let's assume exists somewhere. I haven't talked about cron jobs. Let's assume it's just kind of modeled as a function somehow, and it's going to be able to talk to the state machine, so it takes the state machine as a dependency. We're going to have to run those cron jobs in a separate goroutine somehow. And then the signal catcher I haven't really talked about either, but let's say we have some other thing that's sitting and waiting for a signal, and it's going to have to do stuff when it catches one. So we're going to go all these things and run them in their own goroutines, and then we're going to wait for a shutdown somehow. The question is, how do you do this? Like, what is the craft, the code craft that works here and that isn't like super tedious and can be replicated? So there's a couple of possibilities here, and they all hinge on the idea of how do you terminate these things after you've started them. So for the state machine, it's very clear, right? Our context has a cancellation signal we can call cancel, and then hopefully we've built our state machine such that it respects the cancellation signal. It's not a given, but in our little for select loop, we're selecting on one of those things, so okay, that's cool. But what about all these other things? How do we tear them down? We haven't built in ways to do that, but that's important, right? In order to have good tests, in order to have deterministic programs, we need to have components that are able to be started up and shut down in some coherent way. So it turns out, let's go through these. HTTP listen and serve, there's no way to do it, actually. We have to have a different construction, a different way of expressing that. And I think the way, someone can correct me afterwards if there's an even better way, but I think it's just this two-phase thing where instead of doing listen and serve directly, that's like a helper function, right? And under the hood, all that it does is it binds a listener on the whatever port. Here I'm doing it on TCP port 8080. And then it's calling http.serve, which takes a listener. And http.serve is going to return whenever the listener gets closed. So I can now shut down this little goroutine by calling ln.close. Great. So far, so good. OK, what about our cron jobs? Well, here, we're going to need to wire in some other sort of cancellation. Let's say we just have a cancel chan of empty struct, which has no semantic meaning, so we know what that means. So we pass that as a parameter, and in order to shut the cron jobs function down, we'll just close that cancel chan. Again, that's a one-shot, but since it's just a function, maybe it's OK. We'll do a very similar thing with our signal catcher. We won't get into the details there. But OK, now we have some way of shutting all these things down. We have the go thing on the left and then the terminate on the right. So how do we combine all this stuff together in a way that allows us to orchestrate our entire program in a way that makes sense? There's a couple tools out there. The one that achieved the biggest prominence first, I think, was this package called Tomb. I believe it came out of Juju. Are there any Juju developers here? I think this is Gustavo Niemeyer's baby. It's like relatively old in the Go Apocrypha. It's up to version 2 now. So here's what Tomb looks like. There's a lot of stuff here though. Like there's many methods, and if you dig into it, you see that there's like this. It has this concept of this like two-phase death. So you start all your Go routines in a tomb, and then at some point through some mechanism, it's going to like enter this dying state, and then it's going to go through some like state changes, and then it's going to be killed. And in order to support this, you have to write functions. You have to model the things that are running in the tomb as functions that are take no parameters and return an error. And it is F's responsibility to monitor the tomb and return appropriately once it is in a dying state. And then there's some like helpers that allow you to detect that somehow. So there's like a dying method on it. So okay, maybe if you have like, to me this reads as quite tricky and quite sophisticated. Maybe if you have very specific requirements as to how you need all your stuff to like behave, maybe this solves them. And I'm sure they, in Canonical, they had like use cases that validated all these things. But for me, like, this is exactly what I need. I don't need any like two-phase death stuff, and I don't need this many methods. I want something much simpler. Okay, so let's put that to the side and do a bit more research, and we find that there's actually something called Air Group, which is relatively new. And it's in this Golang org.x repo, which lends it some credibility somehow. I don't know if that's really true. So this is a much better API. It's much fewer methods. That's great. It's a similar thing, though. Like Go, in order to add actors or things into the Air Group, you model them as functions that return an error. And what's not obvious here is like, how do you get these functions to return? How do I pass my listener close or my cancel or whatever? And it turns out that the only way to do this is to use, when you create the Air Group, you have to pass a context. And then it's expected, I think, and maybe someone can correct me if this isn't true, but I think all the functions in the Air Group are expected to like respond to that context cancellation. Is that accurate? Yeah, so like that's great if all your stuff deals with context, but for example, our HTTP listener doesn't have that ability, right? It's just like a net listener. There's no, as far as I'm aware, no like listen with context, and then it will like kill itself whenever the context gets canceled. Maybe that's coming. But there's actually like a large class of things that aren't context aware and that you still want to be able to control in this way, I think. So it's just pointing that out. So like I rubbed my chin like I'm doing right now about this for a little while, and then I realized, this probably isn't as hard as we're making it. So I came up with this other thing, which I think is even nicer. It's only 2 methods, which is 33% fewer methods than even the smaller API, which I think is a good thing. And in the same way that the run style of actor kind of cedes a lot more responsibility to the caller, this also cedes a bit more responsibility to the caller. It has basically, and you interact with it this way. You add actors to it, not as single functions that return errors, but as pairs, right? And so the first function is an anonymous function that runs your thing, and you call that the execute func. And then the second function is an anonymous function that, when it gets run, has the effect of terminating the first function. So you kind of break apart these 2 responsibilities, and you can implement whatever you want in those 2 functions. And then it's exactly the same. Instead of wait, I call the thing run. So here's how it kind of is implemented. I can fit the whole thing on one page, actually. A group is just a collection of what I call actors. The 0 value is useful. An actor is just this pair of functions. That's it. When you add something, you just append the 2 functions to the set of actors. Okay, very simple so far. Oh, sorry, it's 2 slides. My mistake. So here's what the run method does. It does a little sanity check, and then for every actor, it just goes that actor execute func in its own Go routine, and then it's going to send the error value on this channel, which it's pre-allocated to however many actors you have as a capacity. Okay, then it waits for the first error to come. So it waits for the first thing to die or to be killed or whatever. Once it receives that error, then it walks through all the other actors, in fact, walks through all of the actors and executes the interrupt func, and expects that that's going to kill all of the execute funcs. And then it waits for all the remaining funcs to die, and then you're done. So this is it. It's the whole package is like 60 lines of code, but it enables this really nice thing in your func main. So here's how you use it, right? You create this group, 0 value is useful, and then for each thing you want to run, I like this little construction where you like put these little brackets here and you just have this nice lexical scoping because it means I can use ctx and cancel repeatedly for every individual thing. I don't have to give them like special names or anything. It's kind of no point to that, but that's fine. So I have this little thing, and here is where my state machine is going to run. So I have this, the state machine takes a context. That's how I've written it. So I create the context here. In my initial function, I just run with the context, and in my interrupt function, I just run cancel. Okay? Here's how I do my server. And this wasn't really possible in either of the other two, in air group or tomb, as far as I'm aware, not without some like heavy scaffolding. But here, all you do is you bind the listener. In your execute function, you run the serve, and in your interrupt function, you just close the listener. No problem. These two things are the same. The cron jobs and the signal handler both take a cancel chan, so I just create the cancel chan. In the execute function, I run the thing, and then in the interrupt function, I just close the cancel chan. It's exactly the same here. And then at the end, it's just g.run, and then this thing is going to return an error of the first thing that dies. And if everything goes well, the way this is going to be killed is when somebody hits Control-C. And when somebody hits Control-C, the signal handler is going to return with, I don't know, some error that I created. And then it's going to trigger the shutdown of everything else. And in this way, it can control the lifecycle of all the other components. And when any of the other components die, we assume that our program can't run with like in a degraded state with like the storage or the state machine dead. Everything else kind of falls apart. And you see exactly why things fell apart if you want it. So here's my 3 ways of doing orchestration. Tomb, air group, and group is how it's called. Tomb's OK if you have complex lifecycles, but it also has a complex API, I think. Doesn't really work with the listeners. Air group is a small API, which is great, but it only works with context as far as I'm aware. We're moving to a context-oriented world, but we're not all the way there yet, and some things will never get there probably, so maybe that's not so great. Group, it's a little bit esoteric API. I like it a lot because I wrote it, and that's fine, and maybe you can take a look, that's fine too. But it works with net listener style stuff, and I think that's like a great value. So like if there is a moral here, oh, yep, here comes this guy. There he is. Perfect, great. Great. Maybe the moral here is like give more control to the caller. In these examples, we've seen a couple examples of that. But also, you see this in other parts of like the Go philosophy as well. When you're designing an API, what do they always say? Design the API to be synchronous. And if your caller wants it to be asynchronous, they can very easily do it. They can orchestrate it with channels and goroutines if they choose. In the same way, I think maybe we can make the same proclamations about orchestration of components and about actors and about running things. Maybe claim less responsibility in your components, cede more responsibility to the calling context, and you'll have a better time of things. Maybe, I don't know, could be. That's it. Thanks, y'all. Questions? I see a question.
I was just noticing that the layout there, when you showed that architecture graph, it looks a bit like MVC. And I was just wondering if, like, how you decide when to use MVC versus this, or if you just always use this for your.
You're saying MVC?
Yeah.
I've never done web programming, so I have no concept of MVC. So if that's true, then I take your word for it. But yeah.
Any other questions? There was a question from the live stream asking, why not just use context and context cancellation for every single one of those functions?
If you have the freedom to write the function as you choose, then you can definitely do that. But sometimes a context is like more than you care about. Like context comes with values. Maybe you don't want to have to like consider that that's part of the API surface. And for some stuff, you can't do that, right? In a net listener, in an HTTP server, you can't wire in a context, at least at the moment, to the listener. So you have to have some other way, some arbitrary way, I think, to be able to start things up and shut things down.
Hey, so I have a little insight into why you don't do close on the particular HTTP server. So if you want a clean shutdown, aka you never drop a request, right?
Yeah.
That's why you have the tomb two-phase, like dying. Like if there were any requests in flight, you close them out, but you have a million connections open because they're all on keep alive, but 99.9% are idle, so you close those all immediately, but you still have to wait for the in-flight request. So like,
yep.
like I think that is a common pattern, right? So like the
Yep.
two-phase shutdown is a common pattern. So like,
Yep.
how would you handle that? And that's where the listener comes in.
I would like to make 2 observations in response to that question. Number one, we now have this graceful shutdown thing, which I didn't include in these slides due to oversight, but that would be probably the canonical way of doing that these days. Number 2, my group style still enables this 2-phase shutdown in the sense that when you get the interrupt signal for your HTTP listener, you can optionally put information in there, put a close over state in there that allows you to wait for, like, block until all the connections are drained, like send a signal somehow to the API saying, accept no more new connections, wait for connections to close, and then give me a signal back when that's done. You can put all that code in the interrupt closure, and that works totally fine too, I think. Yeah.
Any other questions? Cool. Well, round of applause.